Hi guys, welcome to Computerised Control. Today we are opening a new chapter, the white box. If we use the image of a black box to represent the transfer function in the sense that it is opaque and we cannot see inside, now we are going to do the opposite with a model representation that also describes what is inside the system. For that, besides the usual definition of inputs and outputs of the systems, we need to introduce the concept of internal state X. For instance, if we take an airplane in flight, what is the minimum set of state variables that can at each instant completely describe its condition? We would say something like the velocities and the positions, both linear and angular. I would say at least 6 state variables representing the angular and linear velocities in the 3 axes. Another example with an electric circuit, what are the variables for which you need to know the initial conditions to calculate its evolutions? You're right if you answer the voltage in the capacitors and the current on the inductors, as these are the elements that store energy and therefore have a storage state. In general, if we are modeling a physical system, a good way to have an initial perception about what will be the best candidates for state variables start by looking for the energy-related variables, velocities for kinetic energy, height or spring displacement for potential energy, and so on. As you start modeling physical systems, the intuition to select the state variables will come. So, more formally, we define the state as the minimum set of n state variables that is sufficient to describe a system condition at time k. The next question is how this state develops from time to time, from the condition at time k to the condition at time k plus 1. For that, we introduce the state space model, exactly as a description on how the state will develop in time from an initial condition and possible external excitations. In mathematical terms, how the next state in k plus 1 can be defined as a function of the current state x and the input u, or even time k if the system is time variant. Then, because x is the internal state not necessarily accessible as an output, we need a second equation to describe how the output y is produced from the state, and eventually the input and time as well. The model we have just seen is general, and in general, systems are nonlinear. However, we have an agreement that in this course we would mainly focus on linear time invariant systems. Thus, we introduce the linear version of the state space model where functions f and g have a linear structure defining 4 constant matrices, A, B, C, and D. Introducing the state space elements, first we have the signals. These are the input action, the observed output, the current state, and the future state. And then we have the parameters. The dynamic matrix A, because it holds all the information regarding the internal dynamics. The input matrix B, the output matrix C, and the feed-through matrix D because it's a direct bypass from the input to the output. It is common to depict the state space model using this block diagram that emphasizes the role of each matrix in the overall model. Highlighting the first equation, the so-called dynamic equation, we have the state as the output of a memory delay. If the state at time k is the output of the delay, at the input of the delay we have xk plus 1. Then we just read the equation. Xk plus 1 it's equal to A times xk plus B times uk. So the next state is the sum of the influence of the present state and the external input. The second equation is turned towards the output. the output y is developed from the state x through c, plus eventually, because many times d is 0, the direct influence of the input u through d. Let's now focus on the internal dynamics of the plant. As matrix A relates the future state with the current one, it holds the key for the dynamic characterization of the system. So if we remove the external excitation, the dynamic equation reduces to xk plus 1 is equal to A times xk. This is called an autonomous system. At this point, I review the prey-predator model that we have introduced as an example in the beginning of this course. We have the number of hares, hk, and the number of wolves, wk. Knowing these two variables completely describes the condition of the system at time k. From the modeling process, we got hk plus 1 is equal to hk, and wk plus 1 is equal to wk. Then, naturally, the hares would grow 10% a month, and the wolves would disappear 40% a month. Finally, if they share the same habitat, hares are chased by the wolves with a drop of 20% the number of wolves, and the population of wolves grow 20% the number of hares. We can condense these into smaller equations, or put them in a matrix format, defining the dynamic matrix of a state space model. We have an autonomous system with matrix A well quantified and no external input. Again, if we want to simulate this system, we just need to iterate. Let us take a closer look on what happens if this iteration process. So we have x1 is equal to ax0, then the same x2 equal to ax1, and if we replace x1 there, we get a times x0, and the same for x3 and the same for xk. So at any future instant in time xk, we can get it from the initial condition by multiplying k times matrix A, or A to the k. We define the transition matrix A to the power of k as the aggregation of k multiplications by A. Let us now add the input. If we do the same step-by-step analysis, we come up with a general solution of the system. It's important to say that we rarely use this knowledge at the control design stage, this being more important for the mathematical demonstration of some of the tools we are going to use. One important aspect is the bridge between the state space model and the transfer function model, the two alternative models you've learned so far. Starting by the dynamic equation, we first apply the z transformation and the rearranging terms we get to this. Then the output equation, again applying the z transformation, we finally get the transfer function. So from a set of A, B, C and D matrices, we will get the transfer function of the plant, and this is unique. However, in the other direction, we can get as many different state space representations as we want. For that, we just need to make different definitions of what the state is. For instance, if we redefine the state definitions on the prey-predator example, using the state variables P for the total animal population and D for the difference of hares and wolves, I leave to you as an exercise that we could define a new state space representation of the same dynamics. And we could define as many different state definitions as our imagination allows. Of course, not all definitions make useful sense. A very important chapter of the state space subject is the analysis of the eigendirections. Let's see what this is about. The eigenvectors v are the one directions that verify this equation, AV is equal to lambda v, meaning that if we are at an instant in one of these directions, AV, the direction of the future state vector, will have the same direction as v and scaled by the scalar lambda. These scalars lambda, one for each direction, are the eigenvalues of the system. Rewriting the previous equation, it is direct to see that V is the null space or kernel of the matrix A minus lambda I, the set of non-zero vectors that are mapped to zero. From the linear algebra, the null space has solutions if and only if the determinant of A minus lambda I is zero. Therefore, the eigenvalues of A are the n values of lambda satisfying this condition. At this point, it is interesting to compare the transfer function formula and the null space of the state space model. The roots of the denominator results from this condition, and as we just seen, the null space leads us to the eigenvalues. The first are the poles, the second are the eigenvalues, and it is direct to conclude that they coincide. Everything we knew about the poles is now valid for the eigenvalues. Stability is always the first thing we should focus on. And because eigenvalues and poles have the same meaning, the system is stable if all eigenvalues are inside the unit disk. Exactly the same as for the poles. And of course, we are talking about asymptotic stability. After stability, our main concern is towards the dynamic performance of the system. Let's see how the eigenvalues location will affect this aspect. So here we have the unit disk, and if we have damping d equal to 1, we are on the real axis, and as we decrease the damping factor by 0.9 and 0.8 to 0.7, so you know that 0.7 corresponds to this point here with 5% overshoot, and then we proceed, and you see that as initially you go like in a straight line, the same as you have in the Laplace domain, but then you have this cardioid. And again 0.4, 0.3, and you see that you have some overshoot and some oscillations already, and you proceed to 0.1 until you reach the stability limit. Regarding the time response, you have two indicators, the rise time and the setting time. They are both related with omega n, the natural frequency. And what you have here is their natural frequencies that are fractions of the Nyquist frequency. So as you increase the natural frequency, you're going apart from z equal to 1. And what initially was somehow a semicircle, now it starts going to more distorted curves. So let us see an example. In this example, we start by a block diagram with two block transfer functions. So we have two poles, one in 0.6, one in 0.9, the blocks are in series, and we have 1, 0 at 0. And we can write the two equations in the z domain that describe the relationship between these variables. And here we define an intermediate variable x1 and the output y that coincides with x2, and x1 and x2 will be the state space state. Applying the inverse z transform, we come to the z domain for the two equations, and then by replacing xk plus 1 on the second equation, we get two equations that on the left side have the future state and on the right side have dependencies only on the present state and the input. So if we put these two equations plus the information that the output coincides with the second state, we can put these in the state space representation like this, and I use here blue and red to distinguish the two equations plus the output equation. So we are defining matrices A, B, C, and D for this system, and we can proceed with the analysis of the eigenvalues. So we take matrix A, the dynamic matrix, and we are going to compute the roots of the characteristic polynomial. For that, we do the determinant of A minus lambda I. So if we solve this equation, we get to the information that we already knew because we knew the poles initially, but lambda 1 and lambda 2 are equal to 0, 6, and 0, 9. And the system is stable because these roots are inside. We can also do the simulation diagram for this system. So initially we have the two states with the two delay elements. So if the output here is x1k, at the input of the delay we have x1k plus 1, and the same for state 2. From this point on, we just have to read the equations. So xk plus 1 here is equal to 0, 6 times x1 plus 0 times x2 plus 1 uk. And for the second equation, we have x2k plus 1 is 0, 6 times x1. So we have this relation between the first block and the second block, plus 0, 9 x2 plus 1 times uk. Finally, the output equation states that y is 0 x1 plus 1 x2. So we are just collecting here x2 as the output. Final question is just to note that we did not mention the zeros in the state space model. Fact is that they are not directly visible. This is all for today. Thank you very much for watching. Send me your feedback or press like below. And do not forget to subscribe. Thank you. Bye bye.